Recent advances in AI have ushered in a new compute regime. As models scale, what limits them is no longer how fast a chip can compute, it is how fast it can move data. DeepSeek DSpark is built for exactly this regime. They claim it makes their models up to 85% faster, with no new hardware and no loss in quality. To understand how that is possible and whether the numbers hold up, we first have to answer a simpler question. Why are AI models slow to begin with? When a language model answers you, it writes one word at a time. It reads everything so far, predicts the next word, adds it, and repeats. That loop is why a chatbot can feel slow and why a long answer makes you wait. So why not just add more GPUs? Surprisingly, that barely moves the needle. Generating text is not limited by how fast the GPU computes. It is limited by memory. To produce a single word, the GPU must pull the model's entire set of weights out of memory. It does a tiny bit of math, emits one word, then sits idle waiting for the next load. The cores spend most of their time waiting. This is the memory bottleneck of autoregressive generation, and the fix is not faster hardware. It is a smarter way to generate, called speculative decoding. The idea is to stop writing one word at a time. Instead, two models work together. First, a small, fast draft model races ahead and quickly guesses the next few words. Let us say 4 of them. This little model is cheap, so it is quick, but it is not always right. That is why the big model checks its work. And here is the clever part. Because those 4 words are already written down, the big model does not have to produce them one by one. It verifies all 4 at once in a single pass, loading its huge weights from memory just one time. If it agrees with the guesses, all 4 words are accepted. You just got 4 words for the memory cost of 1. And because the big model always makes the final call, the result is identical to normal generation. The quality never drops. It is a free speed up, as long as the little draft model guesses well enough. And crucially, because the target model always makes the final call, the output is provably identical to normal generation. Speculative decoding is lossless. You get the speed for free with no change in quality at all. But drafting fast has a catch. To guess quickly, the draft model writes all 4 words at the same time, in parallel. The problem is that when you write them all at once, word 4 cannot see word 3. Each guess is made blind to the others. This causes something called suffix decay. The first word is usually a safe bet because it is close to what we already know. But as you go further down the block, the guesses drift and accuracy falls off a cliff. The last words are almost always wrong and get thrown away. So you hit a wall, draft too few words, and you barely save time. Draft too many, and most of them are rejected, wasting the very compute you were trying to save. This is the drafter's dilemma. Push the block longer to save more time, and the acceptance rate collapses. Keep it short to stay accurate, and you barely save anything. Either way, you slam into a ceiling. This is where DSpark comes in. DeepSeek's fix is elegant. Instead of writing all the words blindly at once, DSpark splits the draft into 2 steps. First, a fast backbone lays down a rough block of words all at once, as before. But then, a tiny second module sweeps across the block, left to right, and rewrites each word so it can finally see the ones before it. Word 2 now depends on word 1. Word 4 now depends on word 3. That single sweep repairs the suffix decay, and the tail of the block becomes accurate again. And it barely costs anything. The paper shows that a small, 2-layer DSpark model beats a much deeper 5-layer one that skips this step. It is a structural fix to a structural problem. By letting each token finally see the ones before it, DSpark restores the dependencies between words inside the block. The draft stops contradicting itself, and far more of it survives the check. You might think adding that sweep defeats the purpose. Is not the whole point to avoid going word by word? But the math works out in DSpark's favor. The sweep is so lightweight that it adds barely any delay, under 1.5%. And in return, it buys a big jump in how many words survive the check. Across models from 4 to 14 billion parameters, DSpark accepted up to 30% more words than the leading alternative. In short, more of the draft actually gets used because the words finally make sense together. But guessing well is only half the story. The other half is knowing how much to check. Concretely, tested across Quen models from 4 to 14 billion parameters, DSpark beat the leading drafter, Eagle 3, by up to 31% in accepted length, while adding well under 2% of latency. Checking is cheaper than generating, but it is not free. And this leads to a paradox. On a busy server, thousands of requests fight for the same hardware. If you blindly verify long blocks for every single one, you burn compute on words that were probably going to be rejected anyway. Push it too far, and the whole thing can actually get slower. The hardware saturates. The system spends all its time checking bad guesses, and total throughput collapses. So to stay fast under load, the engine has to be ruthless. It cannot afford to check words that are likely to fail. It needs a way to know in advance which words are worth the effort. And this is not hypothetical. The paper is explicit. Past a certain point, verifying longer blocks wastes the very capacity it was meant to save. More guessing actually buys you less speed. DSpark solves this with confident scheduled verification. It does not just guess words, it scores them. A small confidence head estimates how likely each word is to survive the check. At the same time, a scheduler watches the live server load. When the server is quiet, it allows longer checks to make a single user as fast as possible. But when the server is slammed, it shrinks the check on the fly, cutting the block off exactly where confidence drops. The big model only verifies the words most likely to pass. It is traffic control for computation, never spending a cycle on a word that probably would not have survived anyway. And it is a smooth dial, not a switch. Set the confidence threshold to 0, and it simply falls back to plain fixed-length verification. Turn it up, and the engine grows steadily more selective as the load climbs. So what does all of this add up to in the real world? DeepSeek measured DSpark in production under live user traffic on their V4 models. The result is striking. It makes each user's generation 60 to 85% faster. And here is the part that matters most. It does this at matched throughput. In other words, it does not rob the whole server to make one user fast. Total capacity stays the same, while every individual response speeds up. Engineers describe this as shifting the Pareto frontier. The curve of what is possible between speed and total throughput moves outward, opening up ground that used to be completely unreachable. And DSpark is not locked to DeepSeek's own models. The draft head is model agnostic, bolted onto other model families like Qwen, and it delivers the same kind of gains, unlocking interactivity that demanded far more hardware. The bottleneck, it turns out, was never just the silicon. It was how we scheduled the math running on top of it. Now let us be honest about the numbers. That headline, 85% faster, comes from DeepSeek's own production servers and has not yet been independently reproduced at that scale. The paper is also upfront about a limit. There is a fixed upfront cost to writing that first draft block. If you hand the system an extremely hard prompt where almost every guess is wrong, that cost is wasted, and it can even run slightly slower than normal. But the real lesson is bigger than one number. The largest gains in AI speed are no longer coming from bigger and bigger clusters. They are coming from smarter algorithms, from rethinking how the machine works. Smart guessing beats raw compute,